Hello friends. Today, we have an exciting topic to discuss: patient data analysis with the quantum clustering method. This paper offers valuable insights into the application of quantum computing in unsupervised data analysis. Let's dive in. Before we delve into the details, let's have an overview of the paper. Introduction. The paper starts by providing an introduction to the topic, highlighting the significance of machine learning in data analysis. Evolution of machine learning. It explores how machine learning has evolved and the challenges faced in traditional approaches. Hybrid classical quantum approach. The paper introduces the hybrid classical quantum approach, explaining how it leverages the power of quantum computing in unsupervised data analysis. Experimental analysis. The authors present an experimental analysis of the quantum clustering method, showcasing its effectiveness in analyzing patient data. They utilize a targeted quantum platform for their experiments. Future directions. The paper concludes by highlighting the potential future directions for researchers in this field, indicating the vast opportunities for further exploration and advancements. We will discuss the background of the quantum clustering algorithm, an innovative data analysis technique that harnesses the principles of quantum computing. Quantum clustering is a powerful data analysis technique that utilizes quantum computing principles to perform clustering tasks. Clustering is the process of grouping similar data points together based on their inherent similarities. Quantum clustering algorithms offer several advantages over classical clustering algorithms. Handling large datasets. Quantum clustering algorithms have the potential to handle large, high-dimensional datasets more efficiently. The parallelism and computational power of quantum computing can process vast amounts of data simultaneously. Improved efficiency. Quantum algorithms can provide faster and more efficient solutions to clustering problems by exploiting quantum superposition and quantum entanglement. Overcoming dimensionality challenges. Quantum clustering algorithms are better equipped to handle high-dimensional data, where classical algorithms may struggle due to the curse of dimensionality. Extensive research has been carried out on quantum clustering algorithms. To provide an overview, we have prepared a summary table showcasing the different variants of the hybrid k-means quantum algorithm. Highlight the unique characteristics and advantages of variants. We will explore the quantum computing basics that form the foundation for designing the quantum clustering algorithm. These fundamental concepts enable us to harness the power of quantum computing in the realm of clustering. The first essential concept is quantum data encoding techniques. Quantum computers operate on quantum bits or qubits, which can represent both 0 and 1 simultaneously. Quantum data encoding techniques allow us to transform classical data into quantum states or qubit representations, enabling quantum algorithms to process and manipulate the data. Next, we have quantum distance measurement. In quantum clustering, measuring the distance between data points is crucial for determining their similarity. Quantum distance measurement techniques leverage quantum superposition and quantum interference to measure the distance between quantum states, providing valuable information for clustering analysis. Quantum initialization is another important concept. It involves preparing the initial state of the quantum system for the clustering algorithm. Proper initialization is essential for achieving accurate and efficient clustering results. Quantum initialization techniques set the initial quantum states to begin the clustering process effectively. Quantum centroid calculation plays a vital role in quantum clustering. Centroids represent the center points of clusters, and calculating them accurately is crucial for clustering analysis. Quantum algorithms employ techniques to calculate quantum centroids, utilizing quantum operations to find the optimal centroid positions. Finally, quantum measurement is employed to extract the final clustering results from the quantum states. Quantum measurements collapse the quantum states into classical states, providing the final cluster assignments and enabling us to interpret and analyze the clustering outcomes. Understanding the quantum computing basics used for designing the quantum clustering algorithm is essential. We will explore the flow graph of the proposed quantum clustering algorithm. This flow graph outlines the key steps involved in the algorithm, from encoding classical data into a quantum state to the convergence check for successful clustering. The algorithm begins with the input of classical data. The first step is to encode this classical data into a quantum state, making it quantum ready for further processing. Quantum data encoding techniques are employed to transform the classical data into a suitable quantum representation. Once the data is in a quantum state, the algorithm proceeds to perform distance calculations between the data points and centroids. Quantum distance measurement techniques are utilized to measure the similarity or dissimilarity between the quantum states, providing valuable information for clustering analysis. The next step is the cluster assignment. Based on the distances calculated, the data point is assigned to the nearest centroid. This step ensures that each data point is grouped with the cluster it is most similar to. Assigning the data points to the nearest centroids helps in the formation of meaningful clusters. After the cluster assignment, the algorithm checks for convergence. Convergence refers to the state where all data points have been assigned to their nearest clusters, indicating a successful clustering outcome. If the algorithm determines that convergence has been achieved, it signifies that the clustering process is complete. We will focus on the distance calculation step of the quantum clustering algorithm and discuss how it is performed using the swap test. Additionally, we have prepared a figure that illustrates an example of the quantum circuit used for distance calculation. Let's explore. The distance calculation in the quantum clustering algorithm is facilitated by the swap test. The swap test is a quantum algorithmic technique that allows us to measure the similarity between two quantum states. It compares the input quantum state representing a data point with the centroid quantum state. To visualize the distance calculation process, we have a figure illustrating an example of the quantum circuit used for this purpose. The circuit comprises quantum gates and operations that manipulate the quantum states and perform the necessary computations. In conclusion, the distance calculation step of the quantum clustering algorithm utilizes the swap test to measure the similarity between quantum states. The data points are assigned to nearest cluster. The equation 2 shows the implementation of this process. We will focus on the cluster assignment step of the quantum clustering algorithm. This step determines which cluster each data point belongs to based on their similarity measurements. Let's explore how the assignment of clusters is performed. The cluster assignment process involves analyzing the similarity measurements obtained from the distance calculation step. Each data point is compared to the centroids of the clusters, and it is assigned to the cluster with the closest similarity. To illustrate the cluster assignment process, we have prepared an example on this slide. It demonstrates how data points are assigned to their respective clusters based on their similarity measurements. The clusters are labeled, and each data point is assigned to the cluster it is most similar to. The execution environment of the quantum clustering algorithm and how it is evaluated alongside classical clustering algorithms. The IBM QASM simulator is utilized for running the quantum clustering algorithm, and various evaluation metrics such as accuracy, completeness, and homogeneity are employed for performance assessment. To evaluate the effectiveness of the quantum clustering algorithm, various evaluation metrics are employed. These metrics include accuracy, completeness, and homogeneity. These metrics provide quantitative measures to assess the quality of the clustering results and compare them against existing classical clustering algorithms. By running the quantum clustering algorithm on the IBM QASM simulator and evaluating its performance using the specified metrics, researchers can gain insights into its capabilities and compare them with classical clustering algorithms. This assessment helps determine the algorithm's effectiveness in forming meaningful and accurate clusters. The cluster formation and evaluation process of the quantum clustering algorithm using two specific datasets, the mucormycosis dataset and the cardiovascular dataset. The results will be presented in the form of a table and a figure, demonstrating the successful creation of clusters. The results of the cluster formation process are presented in the form of a table. The table showcases the clusters formed by the quantum clustering algorithm for each dataset. Each data point is assigned to a specific cluster, indicating successful cluster formation. In addition to the table, a figure is provided to visually represent the formed clusters. The figure demonstrates the distribution of data points within each cluster, providing a clear visualization of the clustering results. This visual representation reinforces the successful creation of clusters by the quantum clustering algorithm. Presents the results obtained from the application of the quantum clustering algorithm to a synthetic dataset. The performance of the algorithm will be evaluated using two metrics, accuracy and completeness. These metrics indicate how well the algorithm assigned data points to the correct clusters and the degree of overlap between the assigned clusters and the ground truth clusters. Present the evaluation results of the quantum clustering algorithm on the cardiovascular dataset. The algorithm's performance will be assessed using three metrics, accuracy, completeness, and homogeneity. The results will be compared with those obtained from classical k-means and k-means plus algorithms. The evaluation of the quantum clustering algorithm on the cardiovascular dataset reveals its superior performance when compared to classical k-means and k-means plus algorithms. The algorithm demonstrates higher accuracy, completeness, and homogeneity, indicating its effectiveness in forming accurate and meaningful clusters. Finally, we discuss the significant contributions of the proposed quantum clustering method. The proposed quantum clustering method exploits the inherent advantages of quantum computing. By harnessing the power of quantum algorithms, the method offers enhanced computational efficiency and the potential to handle large, high-dimensional datasets more effectively. One of the key contributions of the proposed method is its ability to address the time-intensive training process. Through the utilization of quantum computing techniques, the method significantly reduces training time, allowing for faster and more efficient clustering. The proposed method demonstrates remarkable scaling possibilities, enabling efficient clustering even with varying dataset volumes. It showcases the capability to handle large datasets, accommodating the ever-growing demands of data-intensive applications. The proposed quantum clustering method incorporates an advanced quantum circuit designed specifically for clustering tasks. This circuit leverages quantum principles to perform complex computations, resulting in improved accuracy and efficiency in the clustering process. The results obtained from the proposed quantum clustering method demonstrate its superior performance compared to existing clustering methods. The method showcases enhanced clustering accuracy, better cluster separation, and improved overall performance in various evaluation metrics. Thank you for joining me as we discuss the significant contributions of the proposed quantum clustering method.